A little bit of information in the same way as it was explained for the contactor and for the solenoid, where you have a small voltage applied, resulting in a larger voltage being switched. Now, in the world of the contactor, all right, just to show you the contactor, and I'll remove the auxiliaries. Our contact block, again, this is not a motor starter because there's no overload attached to this. You need both parts to actually call this a motor starter. So this is just a contactor, and you can't see it because it's not see-through like this one, but there's a coil in here, just like this coil that's here. As I showed you guys when I was showing you this, this is the coil that sits in there. Semi the same, sort of. And so when you energize that coil, you close these contacts here on the front, L1, L2, and L3. And in the world of three-phase, obviously online you guys aren't working with three-phase, it's DC, but same in operation. The three phases closes and sends power to our motor. So in the same way, you get that note here, a small voltage applied to the relay. Now, just to expand on that a little bit, which the book doesn't use, it's another reason why I don't really love this first one, but it doesn't say coil. It should say relay coil. All right. Results in a large voltage being switched. So here in the next sentence, they kind of clarify that a little bit better. There we go. For example, in the diagram that we have above, where we have an input circuit that sends power to the coil, right? There's a symbol of a coil. It's a little bit different. One of the things I would like to point out now that we're looking at it, where it says coil of relay, it has that symbol like the little squiggly, like it looks like a spring. All right, that's one way to represent a coil on the circuit side. But as you can see down here, relay coil symbol used in drawing is like we have seen our symbol all the time for a load, which is a circle with a CR on it. There are other ways to, as it says here, relay coil as identified on the actual relay. On the actual relay, meaning on the actual side of the relay here. All right, and this one, if I can get it to the camera to, sometimes it's a pain with this camera just because, there we go. All right, in this one, let's see if I have, the coil is actually that little square that you see right there, very tiny, but there's a little square right there. Similar to the one that they're kind of showing us here on the far right, where you have that rectangle with a line going across it. So those three might be symbols that you actually see on a relay itself, whereas when you see it on the diagram, it'll look like the circle with the CR in it. All right, and by diagram, of course, we're talking about a ladder diagram. Okay, so going back over to the for example part here, it said applying 24 volts, now they mention coil, to the relay coil may operate a set of contacts that control a higher voltage, in this case 230 volts, but it can control a higher voltage. All right, so that's the first thing. Let's pause it right there because, again, I don't like this use of the word amplifier. It's misused in this sense. So I just want to highlight this part right here. Applying 24 volts to the relay coil, as it said here, a small voltage applied to the relay, results in the operation of a set of contacts that controls a higher voltage, in this case 230 volts, or as it was mentioned up here, larger voltage being switched. All right, so why is that happening? Well, the reason why that's happening is because there's two parts to a relay. All right, and here we'll write these down as notes. There's two parts to a relay. One part of the relay is the input circuit. The other part to the relay is the output side, or the output circuit. If I good time over there. Wonder whose class that is. Let's go watch it. All right, so the input side. The input side is the power coming to the control relay, telling the relay, hey, it's time to act now. So on the input side, what we have is our coil. All right, the coil is on the input side. The coil, and here's again the other reason why I don't like this, is because here it's saying a small voltage applied to the relay coil results in a large voltage being switched. That sounds a little bit like a transformer. Right? A small voltage going in, a large voltage going out. So that's a little bit confusing because this device is certainly not a transformer. So what they're saying is this coil in here could have a low voltage rating. Right? It can have a low voltage rating. And then these contacts here, when they open and close, they can be dealing with a higher voltage. But that's not always the case. All right, specifically for my online students. My online students only work with 24 volt DC. So the voltage applied to the coil is 24 volts DC. And when these contacts open and close, they're turning on a circuit that is also 24 volts DC. The lights in their trainer, the motor in their trainer, everything is 24 volts DC. So the coil can be any voltage. All right, it could be any voltage. It can have any voltage rating. But, all right, this is the important part. It is a fixed voltage rating, all right? Meaning, all right, meaning that this one, like for example, this one is rated for 24 volts DC. That is the only voltage that can come to this coil. 24 volts DC. It doesn't mean that any voltage up to 24 volts DC. So can I apply 12 volts DC to it? No, it won't work. Can I apply 48 volts DC to it? No, you can burn this coil out. It's only rated for up to that 24 volts DC. That's it. Fluctuation of 22, 26, something like that is fine, but not an extreme change. The output circuit is different. The output circuit has the contacts. And here you have normally open and normally closed. You can have 2 sets, 3 sets, or 4 sets of contacts. And we'll talk about the sets. They do have a name. And this is a max voltage rating. All right, this has a max voltage, I'll put it here, rating. Meaning that on the contacts, it's a little bit different. The contacts will be rated for up to a maximum voltage. Like for example, one of the 2 common ones that you'll find on these is either 125 volts AC or 250 volts AC. So for example, if these contacts are rated for 250 volts AC, then I can send 12 volts through these contacts. I can energize 24 volt circuits through these contacts, 120, 240, 208, all the way up to a maximum of 250 volts. All right, so the coil is a fixed, the contacts are up to a maximum. So now going back over to that first. Now this is why, again, this is why I wasn't too didn't really like this first sentence, because it implies that only a small voltage applied to the relay coil is what's applied to a relay coil, a small voltage, and a large voltage is being switched. No, I could actually buy one of these coils that's rated for 240 volts AC. But that's the voltage it needs. I can buy one of these, like in-person students you guys are using, for 120 volts AC. So these come in different voltage ratings, but again, it's a fixed voltage rating, whereas the contacts will have a maximum that they are able to work with. All right, that's the first image. And so again, that's why I don't like this. The relay acts like an amplifier of the voltage or current. You know, doesn't really make an accurate description, especially not when you're first being introduced to a relay. So let's look at the second one. Second one is fine. I don't really hate this one. I didn't really hate the first one, but if you look at figure 8-2, you'll get another example here. Now again, here they're using the word amplifying, which I do not like, but if we look at this circuit, all right, if we look at this circuit, it's actually not giving us a voltage, but the first one did give us a voltage, 24 volt input, meaning the coil is rated for 24 volts. With an output, these contacts are energizing a load that's 230 volts. In this case, we're not getting the voltage, so that's fine because that means this coil could be any voltage. It doesn't really matter. But the point of this one is actually here in this note right above here. All right, it actually is also here, but just in this little part right there. All right, on the paragraph where it says a single input to the relay. And again, when it says relay, just like their use here of just putting a voltage applied to the relay, when they say here also a single input to the relay, they mean the relay coil. Anytime you hear them, or read in this case, read a voltage applied to the relay or an input applied to the relay, it's the coil that is on the input side. So a lot of times it's just a shorthand for saying we're sending a voltage over to the relay, but specifically we're sending a voltage over to the relay coil. So a single input can result in several output circuits being energized. So this kind of acts as an amplifier. This is why they're using the word amplifier. It's almost in the loose, way loose term of the word amplifier. Right? It's just not an accurate use of the word amplifier in a sense. So a single switch can result in a bunch of contacts energizing a bunch of loads. And this gives us an advantage. All right, what this gives us an advantage of is that you can have one single input somewhere. It can be a switch, like the one in this diagram, but it could also be a sensor, right? It can be a timer. It could be anything. A push button start, a sensor. I already said sensor, a mechanical switch, I meant to say. That when it closes, will send power to the coil of the relay, and then those contacts inside the relay are going to react, and then whatever is connected to those contacts gets energized. All right, so it gives you an advantage of a single input, not being forced to control a single output, but being able to control multiple outputs. All right, and so the note is down here. If you did want to pick it up in the paragraph and highlight it, I would just start there. A single input to the relay. If you wanted to even add a note right there saying coil, a single input to the relay coil, results in several other circuits being energized. All right, that kind of ends, like I said, very short chapter. So it ends just the breakdown on that part of the relay. So now it's going to jump over to figure 8-3, where it starts to get into the internal goings-on of the relay. All right, we have a little diagram here. We got some information down there, but I'll bring it over to the whiteboard. All right, and I'll show it in this way, right? This is a close-up of it. All right, so going over to the note. First note that you want to grab here is the first sentence. Usually, they do a pretty good job with the first sentences in this book to just kind of give us a straightforward on what's going on. So what they're explaining here is exactly how we should understand a relay. It is a general purpose component. It is not like the motor starter. A motor starter is not general purpose. A motor starter is designed to start motors. This is not. This is a general purpose switch. It's a mechanical switch, meaning that there are physical contacts inside. All right, they're showing us this contact here. If you look at the drawing in your book, you have the movable armature goes across the top of the coil. You can see the coil down there looks like a spool of wire, or looks like a spool of yarn. You have the contacts that are not movable, right? You have the relay contacts, you have the movable armature. So the idea is this: when the coil is energized, the name of the coil, it says electromagnet or coil. Because the coil is also considered an electromagnet, when you energize that coil, it becomes a magnet and it pulls the movable armature towards it. And that is what closes that set of contacts right there. It requires, you'll notice down here where it says to control circuit. So you have a controlling circuit that sends power to the to the coil, and then you have a power circuit, right? You can see here we have a power circuit going through the contacts. So let's expand on that a little bit. I'm actually going to get rid of that. Let's expand on that a little bit. So how does this show up in our diagram? Well, we have our ladder diagram here, and I'm just going to draw a start-stop. We won't complicate the beginning too much. Put that at least centered a little better. All right, we have our holding situation here. We have our okay. So here's your options when you're building a control circuit. All right, when you're building a control circuit, first of all, you have to try to figure out what it is that's going to go into this circuit. So if it's something very simple, like one motor with one push button start stop, then there is no need for a control relay right now. We can make this load here the motor starter, and yes, we'd have an overload there. I didn't want to add too much. Remember, as we were talking yesterday, we have a momentary push button, meaning when you press it, it sends power to the coil, but as soon as you let it go, it opens back up. So this is why we have attached to the contactor auxiliary sets of contacts that whenever you energize the coil, the contacts also close, right? This closes, and now this provides the secondary route, because again, you are going to let go of this button. Let me just kind of redraw that out, right? You're going to let go of the button instantly. And so you're providing the secondary route. And your motor starts. Press start, energize the coil on the motor starter, close, motor runs. But what if you wanted more on this circuit? What if you wanted some lights here? What if I wanted motor 2 to turn on and motor 3 to turn on, and so on and so on and so on? I wanted to add more and more and more things to this. Well, here's the thing. I can add auxiliary contacts to these motor starters. But the reality is we actually don't like to work with these too much in the field. I mean, they're fine if the circuits are simple. But if the circuits get very big, right, we have more motors, we have 5, 6, 7, 8 motors, we have a bunch of lights that are turning on at the same time, we have simultaneous starting of motors, sequential starting of motors, one and the other, we have timers involved. Once the circuit becomes more complicated, then too many auxiliary contacts mounted on the front of this motor starter, you'll notice it's on the front of it, with a bunch of wires coming to the front of this, starts to make it kind of a pain to work with. All right, that's the reality of these. When there's a bunch of wires here, they're blocking the wires behind it going to the motor, right? These are blocking those. And so we actually don't like these as much when the circuits become too complicated. All right, we actually do not like to use these. Also, they're mechanical, meaning they're attached to the back of this. So sometimes they do get stuck, or this little thing back here jumps, so that little thing right there, which is movable. It moves when this moves here. It'll jump or it'll miss that, and you won't get your auxiliaries engaged. Again, they just present a little bit too much of a problem sometimes when you have too many motor starters. So we don't use the auxiliary contacts, but these are for contacts, to open, to close. If you get rid of them, I got to replace them with something. So here's where the contactor comes in. All right, the contactor shows up because it is separate from the motor starter. All right, it is not attached to it like the auxiliary. If anything happens to the motor starter or anything happens to the auxiliary and I have to replace it, I got to remove a bunch of wires and then take this off and then put the new one in and then attach all of these wires, etc. Just more work extra. Whereas if the relay goes bad, I simply unplug the relay. I just unplug it from where it is, garbage, new one plugged in, control system back on. So when you have a lot of things going on, a lot of loads being energized, bunch of lights turning on with motors turning on, and etc., you get rid of your auxiliary contacts because they present just a little bit too much of an annoyance to work with, and then you replace it with the control relay. So when you have that, going back over to the circuit here, now we sort of redraw this, all right? We redraw this, I'll get rid of all that. So instead of the first thing that we energize being the motor starter, now the first thing that we're energizing is the control relay. Same thing happens when I press the button and I let go of the button. I'm going to kill power to the control relay, so I have to set up a holding contact. In this case, the holding contact obviously cannot come from the auxiliary because I got rid of it. So that is going to be one of the contacts inside the control relay. So this is our input circuit side. Going back over to the diagram, just a little bit different from the one that they have here, where they're showing us here the control circuit with that switch. That switch is being replaced with this push button setup, with the holding contact or seal or latching relay or latching contact. Now from here, we use another one of the contacts inside the relay on another rung to now energize the motor. So this will be, now I could also make this a little bit easier if I don't want to waste a contact on the relay. I could also simply put the motor starter here and just kind of use this contact that's already there. I can just piggyback from it. The way I would wire this up is push button to control relay, contact to control relay, and then control relay over to motor starter. That would be a way to wire that up. You have a few options on how to wire this. Remember what I said last week. Whenever you put a little dot here or a little dot here, I am now giving the person who's wiring this up the ability to wire this up however they want. Whereas, and this is why I did it this way, in this method here, there's no choice. You're coming from this contact with this wire. Now, if I want to start motor 2 at the same time that I start motor 1, then I simply grab another set of contacts from the control relay, and now I have motor 1 starting, and at the same time, I have motor 2 starting. So this is a way to set up a relay system. One of the good things about this relay system, to use it like this and not use the auxiliaries, is again, if anything happens to the relay, it is an easy replacement to switch these out and put one back in. So let's just write this out so now you can understand visually what you're looking at here. This is the input. All right, this is the coil receiving electricity, and these are the outputs. Now you will notice in this circuit, what is the one thing that you notice here? And that is that the voltage, whatever voltage is going to the input circuit, is also the same voltage running through the output circuits. So in this case, we have the same voltages going to the input and the same voltages running through the outputs, which is a lot like the way your labs are constructed. All right, but they don't have to be. I'll show you a different setup. Let's say I have $120 volts over here. Let's say I have a transformer setup. 120 volts, meaning that we have hot on this side and we have neutral on this side. And down here we have our power supply that's stepping down from 120 volts AC to, let's say, well, let's go with 24 volts AC. All right, so we have a 120 to 24 volt. Technically, that's a transformer, so actually let's do a power supply, which, let me just make this a little bit bigger for space purposes. Let's do 120 AC and stepping this down to, just like the ones in the labs, 24 volts DC. So now we have a second circuit coming out of this with L1 and L2. So this is another way that this can get constructed, where I have my push buttons energizing the control relay coil holding contact from the control relay, but the motor starter happens to have a 120 volt coil. Let me move that over just a little bit. There we go. This contact up here is also from the control relay. Same control relay has multiple contacts inside. We'll go through how many and all the different setups. But as I said, going back over here, we have 2 sets, 3 sets, and 4 sets of normally open and normally closed. So if you have 3 sets of normally open and 3 sets of normally closed, you have multiple contacts. So here I'm using 2 of them. 2 of the available normally open contacts. And now I have 2 different things going on. I have the input circuit down here at 24 volts DC, meaning the coil inside, just like this one, is rated for 24 volts DC. Oops, there's my coil there. One of my contacts is also 24 volts DC. This is an output though. And the other output over here is on the 120 volt side. AC, of course, but. So one contactor, 2 different voltages going through it. All right, one for the coil, that one cannot be changed. In other words, we cannot put this coil up here on the 120 volt side. It is rated for 24 volts DC. That's the voltage we have to apply to it. Motor starter contactor that I am using However, that one does have a 120 volt coil, so I have to energize it with 120 volts, meaning that the contacts inside here are dealing with two different voltages, 24 volts DC, 120 volts AC. As I said, going back over to the first set of notes that I gave over here, it has a maximum voltage rating, so as long as I don't go past the maximum, I'm okay. I can be as low as the lowest, or I can hit right up to the maximum. And I can run 1 volt through it, or I can run up to 250 volts to it. All right, so coming back over to the book. All of that is down here. Everything that I've just explained is down here. All right, so let's highlight it a little bit and just get an idea of what's going on. Again, general purpose relay, mechanical switch operated by a magnetic coil. That coil is available in AC or DC design. All right, these relays are available with coils that can open and close contacts ranging from a little bit of voltage up to several hundred volts, as I said, up to the maximum the contacts are rated for. Now it is telling us a most common, I can accept this. 24 volts, 12, 48, 120, they have 115 here. 230 they have, or 240 they have 230 here. Remember, because Florida exists, I think I explained that to you guys, where Florida's 110, 220. You guys are 120, 240. So for engineering purposes, they just use 115, 230. Just right down the middle for both. They are also available in DC voltage. All right, and as it says here, these relays are available in a wide range of switching configurations. Wide range is a stretch. 2 sets, 3 sets, 4 sets. Wide range is a bit of a stretch. So and the reason why I explained it the way I just did right now is because this isn't so straightforward as to what I have here, at least that I feel I have here, which is inputs on one voltage, outputs on another voltage, or everybody on the same. Okay, now to how many we get. All right, there are 3 types. These are the most common, I would say. All right, the most common ones are 2 sets, 3 sets, and 4 sets. All right, the one that I have here, shown here, is the one that, if I'm not mistaken, is used for in-person labs when you're using the 120 volt AC, and it's an Allen Bradley. That's what we use at the school, although we are introducing Siemens soon. So there's 2 ways to understand this relay. All right, one is the coil. All right, we have a coil voltage. And this coil is going to have 2 pins on it. Actually, let's not do the pins yet. Pause there for 1 second. So there's the coil side to this, but then there's the contact side to this. Sorry, I didn't mean to erase that. So when you go to order one of these one of these control relays. When you go to order one of these control relays, they're going to ask you for 2 bits of information. All right, I call the supply house, like to order a control relay. First question they're going to ask you is, what is the coil voltage rating? What type of relay voltage do you want? When they tell you what kind of relay voltage do you want, they're not talking about how much voltage is going to be running through your contacts. No. They want to know, what is the coil voltage rating here? So you will tell them the coil voltage rating, 24 volts DC, 120 volts AC, or whatever in between. The next question they're going to ask you is, how many contacts do you want? All right, and as you see on this note here, it says there are 2 sets of contacts each with a normally open and a normally closed option. So the two types of contacts that we are, sorry, the three types of contacts that we have are single pole, double throw, two pole, double throw. Sorry about that. Yeah, sorry about that. Two pole, double throw. Three pole, double throw, and four pole, double throw. Sorry, I meant to erase that. There we go. That's what threw me off. The single pole, double throw threw me off. These are the three types that we have. Two pole, double throw, three pole, double throw, and four pole, double throw. Now, why are they called this? Because each one of your contacts inside the relay is, and this is why I had the single pole, double throw. Actually, I'm going to move this over to the side a little bit, just moving it over here. One set of contacts to the relay is a single pole double throw switch. What is a single pole double throw switch? Just like the one that I showed you yesterday for the input devices, it looks like this, where you have a single pole in and a double throw out. Two double throws. Now the reason the relay sets it up this way is to save space. All right, but what this is actually is one normally closed set of contacts and one normally open set of contacts. So in a single pole double throw setup, you have one normally closed set of contacts and one normally open set of contacts. Now, let's erase this. Meaning now that in a two pole, and I'll put it sideways here, in a two pole double throw setup, I have two single pole double throw switches. Oops, there we go. Meaning I have one, two normally closed set of contacts. I'll do it in a different color here. One, two normally open set of contacts. This is the one that you see here. All right, one normally closed, one normally open, one normally closed, one normally open. In a three pole double throw, well, you have three of them. Oh, sorry, I don't have it there. You have a third one. You have a third single pole double throw switch, and so you have three normally closed and three normally open, and then guess what? In a four pole double throw setup, you have four of these single poles, and again, one closed, one open, for a total of 8 contacts. 4 of them normally open, 4 of them normally closed. All of them, now going back over to the note that we just had here. Sorry, was a note here. Apologize, going back over to one. Okay, where was the note? Sorry, I lost the note. 1 second. Oh, it was a note that said at the same time. I lost that note. I believe it was... Oh, sorry about that. I have lost where the note specifically that I was wanting to point out. But anyways, going back over to the idea here, I have one coil and I have 8 sets of contacts, 4 normally open, 4 normally closed. So when I energize that coil one time, all 8 of these contacts react at the same time. That was the note that I was looking for. I have lost this note, the at the same time note. But that's the idea. All 4 of these contacts are going to close at the same time. All 4 of those contacts are going to open at the same time. Everything that is normally closed right now is the direction the voltage is running through. So the voltage is running through that one. The second you energize the coil, the normally closed ones will open, meaning now the contacts will go this way, and now the voltage is redirected through the normally open set of contacts. So let's clean up this and just make sure that we understand. 2 normally open, 3 normally open, 3 normally closed, and 4 normally open, and 4 normally closed. So it depends on the application and what you want to do with your, going back over to the diagrams I have here. Here I only have use for 2 of them. 1, 2. So maybe I'll just buy a 2-pole double throw. Maybe I'll buy a 3-pole double throw, have an extra one. Over here I have 3 of them. So I for sure need a minimum of a 3-pole double throw. But again, I can buy a 4-pole double throw and take advantage of 4 normally open contacts. We haven't even used the normally closed yet. Now, what if I need more than that? What if I need another 4 normally open, normally closed? Well, here you can set up a second control relay number 2, control relay number 1, and then take advantage of the extra contacts the other control relay has. How many control relays can I add to a circuit? As many as you need. The idea behind a control relay going into a control circuit is to take advantage of the fact that it has a bunch of normally open and normally closed contacts. Now I say a bunch, but it is limited to 4 of them. So if I have, let's say for example, 8 motors that have to all start at the same time, then I'm going to need 8 normally open contacts. If I also want 4 green lights to turn, or 8 green lights to turn on at the same time for each of the motors, then I'm going to need more normally open contacts. And here's where for lights, then yes, for lights, you can throw in some auxiliary contacts to help you with a green light, red light turn on the way we've used it in the labs. It's okay. I'm not saying don't use an auxiliary set of contacts. They do have a place. So now think about it. You're looking at a control relay where you have a bunch of a bunch of control relays going into the control relay. Control relay 1, 2, 3. I've opened up control cabinets and seen many of these in there. 2, 3, 4, 5, 6, 7, 8 of them. So imagine 8 4-pole. It gives me 32 normally open contacts. I got a bunch of motors in the control panel as well. A bunch of auxiliary contacts for all the lights also. So that's one way to start to build a control circuit where you need a lot of uses for contacts. Throw in control circuits. You throw in control relays. Yesterday I showed you that you could also put contacts behind push buttons. Right? You can put 2 of them, an open one, a closed one. I told you you can even stack on top of those to add more contacts to the control circuits for extra things. So just to fast forward, at some point somebody was like, well, how many of these control relays are we going to put into this control circuit? I need, let's say a 4-way traffic light system where I have 4 lanes. on each four corner. I have 4 times, I have 16 lanes. That means I have 16 traffic lights. 16 of those traffic lights. 1 light, 2 light, 3 light. I have 16 times 3 now. Every one of those lights to turn on and off requires a normally open contact. So do the math. I'm not going to do the math in my head right now, but 16 times 3, whatever that is. What is that?
48.
48. I need 48 normally open contacts. So I got to have 48 control, well, not 48, but divide that by 4 and
12.
12. I need 12 of these in your amazing math, by the way.
No, I was doing it while you were
You're a
talking.
supercomputer. Okay, you're. Are you AI? So you need 12 of these. And that's just for these things. If you need any other function to happen, you're going to need. So at some point, somebody said, you know what? Let's build this PLC. And a PLC advances us into a next stage where the smallest PLC, which you're going to work with next module, it's the SLC 500 or the Allen Bradley 500. It's the smallest one they make only because it isn't less of a PLC. It just has less contacts internally. It gives you 100 contacts. All right, the ability of 100 contacts, and they're not physical. They're not physical contacts. This is the crazy part of it. They're not actual physical contacts that are opening and closing that you can visually see open and close, and you can grab your meter and measure continuity. They're inside the computer. And the computer outputs send voltage to the different loads, motor starters, and lights for traffic lights. So that's why these days in these larger traffic light systems, you'll open up a control panel to a traffic light, by a street, it'll have a PLC inside just because there's so much need for more and more contacts. And the more physical control relays that you put into, the more auxiliaries, it's just more physical wires. The PLC having the contacts internally removes the use for all of those wire installation, and it just really advances the way we can set up a control circuit with minimum hardware, which also leads to less troubleshooting headaches. Because as you've noticed now, if you've troubleshot a little bit on your labs, if you're tracing down wires, it is just very annoying. But if you have a simple control circuit, 2-3 motors starting, a couple of green light, red light systems, okay, relays are still perfectly fine, still used. Your PLC teacher, the one Fred that sets us up, he will tell you next module, everything you can do with a PLC, you can do with relays. You just need a lot more relays. And you need somebody that knows how to wire stuff up. All right, so this is one of the ways that you will order your control relay. Again, we're back to me just calling the supply house. I need a control relay. Again, first question is, what is the voltage to the coil that you require? I will say the voltage to the coil required, and then the next question is, how many contacts do you need? So I'll tell them, I need a 2-pole double throw, a 3-pole double throw, or a 4-pole double throw. Now, the other way that this gets explained on the relay, and we're going off book here now, the rest of the stuff here in the book, I'll come back to it for a second, but unnecessary to continue. I just need the relay. The other way to talk about the relay and its contacts is involving the pin setup. All right, the pin setup back here. Now, here's what I will say about this pin setup. All of you guys are working with our Allen Bradley. This Allen Bradley, and some other relays have this as well, has this style of contact. So it's kind of easy to read which one is the normally closed and which one are the normally open. But you also need to know how to read the pin setup. All right, the pin setup is also something to just simply learn. It's very easy. One of the ways I just like to show you how to do it is, the first thing you want to do is just kind of locate your coil, which is the 2 and the 7. and then everything else is part of the contacts. All right, 2 pins are always, as it says here, pins 2 and 7 are for the coil. So 2 pins are always set up in your pin setup for the coil. And then, if you have one set of contacts, those are 3 pins. In this case, the 1, the 3, and the 4. And if you have another set of contacts, you need 3 more pins. Here is the 8, the 6, and the 5. All right, if you look at the switch that I have that is here, it is like the single pole double throw switch that I just drew for us. So this one has 2 of them. Let me minimize there.
So if this one had more contacts, would it have more pins?
Yes, exactly. Let me show you. This is why I pulled this one. I knew there was a reason why I had this one. Same thing. First thing you want to locate is the coil. In this case, the 2 and the 10. And the rest of these are contacts. The 1, 3, and the 4. Allen Bradley mixes, uses the same overlapping numbers sometimes, like 1, 3, 4. The 6, 5, and the 7. And the 11, 8, and the 9. All right, so now this one is a 3-pole double throw with more pins. I'm going to teach you how to understand the pin setup. Because sometimes when you order these online, like if you're talking to a human at a supply house, a little bit different because, they can always help you and walk you through stuff. Sometimes we do, get an operator. Let me pull one up here real quick. Sometimes, you get an operator, and that's always nice when an operator comes up. Let's see here. Just wanted to pull one up as if we were ordering it. Just to see what they're using. All right, just to see what they're using to let us know how many contacts here. Let me see. No, they're not giving me the specs here. That's annoying. Let me see. Let me try Granger. See if Granger will show me one. Let's see, Radwell. Here we go. All right. Okay. So here, for example, if I wanted to go order, this is our Allen Bradley, same, right? Here's our Allen Bradley setup. It's the same one we have. This one's 24-volt DC coil. You can see right there from the 1314. And this one has, you should be able to see that fairly okay. It has more pins, right? It has more contacts. So this is a 4-pole double throw. And if we come down here, it does have both bits of information. It is saying 4-pole double throw, right? It has the 4PGT here, 4-pole double throw. And then it's saying 14-blade terminal. All right, this is another way to say pins. Sometimes they call them blades. Sometimes they call them pins. The ones we're using are pins. All right, the ones back behind this one, they're not showing me. I can't tell, but sometimes they have little blades on the back. Whereas ours are actual pins, all right? These are actual pins going on back here. So this one is a 14-pin or a 14-blade system. All right, as you can see, 24-volt DC. That's the coil. It doesn't say it's the coil, but that's the coil. This is not the amount of voltage the contacts can hold. The contacts can hold probably 250 volts. Usually 125 or 250, but I think everybody, for the most part, orders 250. That would be information that the relay would tell you on one of the sides of the relay, but I can't really get that information too well from these pictures here. All right, it doesn't say the rest on that one. If I ordered a 3-pin, then the 3-pin would be different. Okay.
So on this one, for the top three green dots, which one would be normally closed? Because it looks like there's a dash between both.
Yeah, it's a little bit hard to read, but it's leaning towards that side. And then this one is open. It's a little bit hard to read on this one. So let's get rid of that. That would be the... Here's the other thing. That's a good question here because it brings up something else, which is identify the common.
Oh, 369.
Right, when you have a 3-pull double throw switch, technically you have a common and a normally closed and a normally open. So one of the first ones you want to also identify, and this is just the way I like to read these, but is to identify the common. So in this case, the 6 is the common. In this case, the 11 is the common, and in this case, the 1 is the common. And yeah, you pointed out that it's hard to kind of read that one. So the 6 and the 5 here are the normally closed ones. The 6 and the 7 are the normally open. So if we were numbering this one, it would be 6, 5, and 7. That's one of them. And then the other set, 1, 3, 4, which is a common one. And 11, 8, and 9. That's the 3-pin setup.
Why can't they make the numbering easier?
Here's the worst part about that is that looks awesome as far as being able to see it. When you get to be my age and nice and blind, and then you're trying to see, there's the pin setup. Hold on 1 second. Let the camera adjust. 1 second. Let the relay take over the whole. Come on. Adjust. Maybe it's my fingers. Well, you should be able to see it fairly okay there. I really wish it would just center. There we go. There we go. There we go. So there's the pins right there, right? There's the pin setup. Let me turn that this way. So it's hard to see it, or I should say, it's even harder to see it here. All right, this is the 11 pin, which is the one that you're looking at on the board here. There's the 6, the 7, and the 5 right up top. That's a little better to see, I guess.
Yeah, it's touching them now at least.
Yeah, you can see at least right there. Yeah, you can see these right here. And then you can see, like I said, the coil right on there. So it's a little bit harder. And then, well, and here again, now I'm zooming into a camera that's high definition. Even though it sometimes has not great, but it is high def camera. If you're in a control panel inside of a, distribution center where the lights aren't that great above you and you're trying to see that and you're just, what in the, get a flashlight. Because this one doesn't have the contacts on the front. I don't get any information about the contacts here. I only would have to see it on that top system here. So there's a way to understand the pins. All right, there's a way to understand the pins. First, I'm just going to put them here. So remember, you have 2 pins are always for the coils. 1, let's just draw this again. 1 pin, 2 pins, 3 pin. So 1 single pole double throw is 3 pins. 2 single pole double throw would be 6 pins plus the 2 for the coil. All right, I'll leave that there. So 2 times 3, 6 plus 2 for the coil. 8 pin. All right, 2 times 3, 6 plus 2 for the coil. Same thing here now. 3 times 3, it's always 3. It's always 3 times something. 3 times 2, 3 times 3 equals 9, plus 2 for the coil. 11. So this one is an 11 pin. And then same thing when you get down here. 4 times 3, 12, plus 2 for the pins. 2 for the coils. 14 pin, which is the one that I just showed you online. All right, so I'm going to erase this. You will need to be able to identify, and now we're talking exams and such, what type of relay has 2 normally open, 2 normally closed, and then multiple choices of pins. 8 pin, 11 pin, 6 pin, 14 pin. Or how many pins does a 3-pull double throw have? All right, so be able to match the throws and pins to the correct amount of normally open and normally closed contacts that you get. That is the most important part, aside from knowing what the coil voltage to your relay has to be, because that's going to be the first question they ask you. And then the second question they ask you is how many contacts do you need, or pulls versus pins. What kind of pins? They might ask you either one. If you're ordering online, which 9 times out of 10 these days, everybody is just going online to Grainger, ordering, or whatever supply house, and ordering. So you'll need to be able to identify it by the pin setup. So the last thing is, because they do mention it here, when we're troubleshooting, only that you have to now remember that because you have a control relay where you could potentially be on 2 different circuits, you have to keep that in mind when you're troubleshooting. Your digital multimeter might be on, like they have here. They have it on the 115 volt side, the contact heading to the solenoid, but the coil that's being controlled by the flow switch is on the 24 volt side of things. Just like what I have here. You're troubleshooting half of this circuit, trying to figure out why the motor starter is not energized. Your meter needs to be turned to 120 and measuring. You're trying to figure out why the coil's not energized. Your meter now needs to be on DC. So also be able to identify that as well. If you get a diagram that has 2 different voltages, and the question is, if I'm troubleshooting on the motor starter, what voltage should I expect, etc. All right, be able to identify the voltages on the control circuit in a troubleshooting scenario. If you got both of those, that's going to wrap us up.